And today we will use transformations to define what we call the forward kinematics of a robot. And in order to do that, we have to define some terminology: what are joints, what are links, degrees of freedom, and other aspects of modeling a robot. So we will start with the description of a robot. We'll talk about degrees of freedom, what is the work envelope, what kind of joint types we have, what are the links, and eventually we're going to use all this information together with what we learned last week to define the forward kinematics of a robot arm. Very quick recap what we saw last week. The final form of the transformation matrices, what we call the homogeneous transformation matrices, 4x4 matrices which can describe translations of two frames relative to each other, or rotations of two frames relative to each other, or any combination of the two. Right? We saw that in order to combine subsequent transformations, we do matrix multiplication between this kind of matrices. If V0 represents a frame with respect to another frame, a reference frame, we can transform it by multiplying with a transformation matrix, let's say the rotation around X, right? And we saw we can do this either by multiplying from the left or from the right. The resulting transformation is slightly different. So for instance, if we multiply from the left, we have a rotation around the reference axis. Right? So the reference is the thin frame here, so we have a rotation around the thin x-axis, which results in a translation and a rotation at the same time, right? While if we use the same transformation matrix and we multiply it from the right, now we have a rotation around its own frame, or around its own axis, right? So that's the difference between left and right multiplication. We will come back to this many times. You practice a bit in the lab, and this week, next week, again, we will come back to this concept. All right. We also saw how we can use transformation matrices to change the reference of coordinates. So for instance, if we know what are the coordinates of a point in space with respect to one frame, let's say frame 1, that we call P1, okay, coordinates of point P with respect to frame 1. All right. If we want to transform these coordinates to another frame, so we know what are the coordinates of the same point but with respect to another frame, let's say we want to know it with respect to frame 0, we can do this if we know the transformation of frame 1 with respect to frame 0, which we call R01. Or another way to think R01 is the transformation that takes us from frame 0 to frame 1, the action of movement. All right, and we also saw, and you practice in the lab, how we can also express a pose or a reference frame that we know with respect to one frame, transform it to another frame. So similar logic. Let's say I know this transformation, as you saw in the lab. I know where is the box relative to the camera in this graphic, right? And I want to know where is the box relative to Vasilescu, right? If I know what is the transformation from the Vasilescu to the camera, or how is the camera, what is the pose of the camera with respect to Vasilescu, I can calculate what I need using, again, multiplication, right? A quick mnemonic to remember these things is, okay, if I know transformation, let's say, from one frame to another, and I know what is the transformation from a third frame to the first one, then I can calculate what is the transformation from the third frame to the second one. Like I sometimes think of it as fractions, you know, where I can simplify this indices. It's not, you know, the most scientific way, but it works practically. All right. So going back to the big picture that I presented last week, we want to go to great robots. We did the first step. We defined transformations, and today we're going to talk about kinematics, and more specifically the forward kinematics, a part of it. Right? We're going to do the part one of forward kinematics. All right? Great. So in this course, we will mainly talk about this kind of robots, robot arms, or manipulators, or articulated robots. Where they basically, the characteristic of these kind of robots is they have a fixed base, somewhere mounted on the floor or on the wall or somewhere that it's relatively fixed, right? And the robot can reach different parts of the environment by moving joints, right? So we have several joints that they can move, and the robot can reach different poses, right? As I say, we mainly talk about this kind of robots, and towards the end of the course, we will also talk about other types of robots, and we'll see the same models for other types of robots. Right. There are two main parts of robot arms. First thing is what we call a link, which is the structural part of the robot. Right. You can think of the hardware, the metal parts or plastic parts or what material it is. It can have different shapes based on the design of the robot, different sizes, different configurations, and they're typically rigid, meaning that they don't deform, right? So we don't consider that they are moving. Of course, nothing is super rigid in real life, so there is some kind of motion, okay? But we neglect it for our modeling. All right? Now, links are combined using joints. So that's the moving part of a robot, right? And we have two types of joints. There are more types of joints, but in robotics, usually we have these two types of joints. Out of the two, the most popular one is what we call the revolute joint, right? It's basically a joint that allows motion around, a rotation around a fixed axis, right? Just a rotation around one single axis. You can think of it as a hinge, like the doors have, or like, I don't know, like your elbow, where you have just one rotation around an axis, right? You might be tempted to call it a rotational joint or things like this, but the official name or the proper way of calling it is revolute. All right. As it's mentioned on the slide, we say that these kind of joints can add 1 degree of freedom to the robot. We'll talk about degrees of freedom in a second. Probably it's something you have heard, and we'll see more details about it. Right. So this is the first type of joints that we see in robots. The second type of joint is what we call the prismatic joint, where this kind of joint allows motion, a translation along a fixed axis, right? With the revolute, we had a rotation around the fixed axis. With the prismatic, we have a translation, right? Try to depict it here. Basically, this green part can only translate around on this axis relative to the parent, right? The red one. All right. Again, this kind of joints can add 1 degree of freedom to a robot. You've probably heard this idea before, degrees of freedom. Any idea how we could describe it? What is a degree of freedom of a system, or in this case of a robot?
How many types of movement a thing can make?
All right. How many types of movement? Okay. Other definitions? It's not wrong.
How many axes can we perform certain movements?
All right, kind of the same story, right? So it's like you're thinking of, I don't know, space, 3D space, and then, okay, in how many different ways an object can rotate or translate, right, in space. More generally for systems, I don't know, it's the way a system can change its states, different, how do you call this, different axes that it can move along. It can be movement, but it can be other things, like maybe you've seen degrees of freedom in other contexts as well, I don't know. Different fields have different context. All right, but in our case, yeah, it's about movement, and it's about basically how many along how many axes can an object rotate or translate independently from the other axis, right? So this word is very important, independently. Like, okay, I can move along X axis, but can I do it without moving along Y or Z axis? Yes?
For example, a screw only has 1 degree of freedom, right?
Right.
Although it revolves around an axis and it translates.
But it cannot do it independently. Exactly, that's the idea, right? The moment you rotate the screw, you also translate. So the movement between translation and rotation is coupled, right? You can describe basically what would be the state of the screw, the rotation and translation by using just one of the two variables, right? Great, that's exactly the idea. So it's the same with robots as well. We typically refer to the way the end effector of the robot can move independently, right? Because the robot has different parts that can move, but we care about the end effector, right? So how many of the positions and orientations of the end effector of the robot can we change independently, right? So for instance, we saw in the first course, we had these Cartesian robots or a planar robot where it has two revolute joints, which look basically something like this. So here we have two joints. First joint here and second joint here. They both rotate around axes that come out of the screen. So basically on this plane, right? And for this kind of robot, we can show that we can change the X and Y direction. Let's say if this is Y and this is X, we can change both of these coordinates of the end effector independently, right? So here I try to show it using some animations. So here I can change, you don't see the bottom part of the robot, but you can imagine, right? I can change just the X coordinate, which would be this direction, the X coordinate of the end effector without changing the Y, so without going up and down, right? Let's see if I draw a line here. Yeah, I cannot draw a line straight, but more or less you can see that I'm on the line, right? And I can also do it for the Y direction, right? I can move up and down without going left and right, right? This means I can change one of the two coordinates independently, right? Now, we said that degrees of freedom have to do with how many different movements, different axes I can translate or rotate along independently. Since we have a robot that can just move on a surface, a planar robot, how many possibilities do I have? What is the maximum number of degrees of freedom I can reach? So what is the maximum ways that the end effector can move? We saw that we have the X translation, the Y translation. What else could I change? Degrees of freedom, it's about translation and rotation, right? Can I have another translation? It's just x, y. I cannot move on the z, right? Because I'm on a plane. There's no z. Right. So what's left? So we have 2 out of the two translations, right? Do I have any rotations?
I can rotate along this axis.
Right, and the vector can rotate around this axis, right? Can it rotate around any other axis? Can it do this? No. Can it do this? No. Right, because I'm on the plane. So basically, if I'm on 2 dimensions, I have maximum 3 degrees of freedom. And this robot basically we saw that it can move the x and y independently, but if you see, it cannot maintain the same orientation while doing the x translation, for instance, right? So it can change x independent from y, but it cannot change it independent from, let's say, orientation theta as well. Right? It's the same thing here. It can change y without changing x, but it has to change the orientation, right? So how many degrees of freedom does this robot have? 2, because I can change 2 of these things independently. I could have made animations as well that I can change x without changing orientation, but then I would have had to change y, right? There's no way that a robot with 2 joints can change 3 degrees of freedom. And that's what we saw here. Each one of these joints can add 1 degree of freedom to the robot. In order to have a robot with more degrees of freedom, I need to add more joints. Right? If I have 1 joint, I can have up to 1 degree of freedom. If I have 2, I can have up to 2 degrees of freedom, and so on. If I add 1 more joint, we can add 1 more degree of freedom, right? So if I have this kind of robot, right, with 3 joints, then I can change x independent from y and theta, the orientation theta, or y independent from x and theta, or theta independent from x and y. How would that look like? I would be able to just rotate without changing the coordinates of the end effector. Right, so this manipulator can vary x, y position and orientation independently. What happens if I add 1 more joint on the plane? So the same joint as these ones. Since I'm constrained to be on the plane, let's say I do this thing. And the end effector is now here. Will I have 4 degrees of freedom? No. Why not?
Because it's again a rotational joint. So I have 4 rotational joints.
So? Can only move on the plane. I cannot have more than 3 degrees of freedom. There's no other way I could move on a plane, right?
Maybe rotational, but
on another axis, so it's not on the plane anymore, right? Exactly. So the robot becomes more dexterous. It can move in more ways, but the degrees of freedom are still 3, right? Because I cannot have more than 3 degrees of freedom on a plane. I cannot move in a different way besides translation on x, y, and rotation. So in that sense, on the slides with the joints, it was saying it can add a degree of freedom. It doesn't mean it will add a degree of freedom, but it can, might or might not, depends on the design. Now, how do we calculate the degrees of freedom? There is a formula that's also explained in the lab, where we have basically the n being the number of links that I have, or number of joints. It's kind of the same thing, right? And C1 is the constraints a joint adds on the robot, right? Because a joint, basically, we can think of it as adding 1 degree of freedom or constraining the motion in some degrees of freedom besides, I don't know, in this case with a prismatic and revolute in one joint, right? So this kind of joint constrains the movement along all 5 degrees of freedom besides one rotation, right? And this one constrains 5 degrees of freedom, 3 rotations and 2 translations, and leaves freedom in one translation, right? So this C in this formula is the number of constraints a joint adds. So in our case, it would be 5 for both of them, right? So if I have here 3 joints, let's say I have 3 minus 1, 2 times 6. 3 minus 1, 2 times 6, 12. Okay, I got blocked. Plus 5 plus 5. So there should be a minus there. Yeah, I think it should be a minus. So that we end up with 2 degrees of freedom. All right. I'm not spending too much time on this. We'll discuss more about it in the lab as well. The idea is that by adding joints, we can make the robot more dexterous, can reach more configurations. And this also, the constraints, yeah, the C1 also depends on the how the joints are oriented. So it's not just the number of joints, it's a bit more complicated than that. All right. Now, another thing that defines that the number of joints and the arrangement of the joints defines is what we call the work envelope, which is basically the volume that the robot, the end effector of the robot can reach and operate, right? So as we say, these kind of robots, they have a fixed base. So naturally there is like it's not an area, it's a volume around them that these robots can operate, right? They cannot go wherever. And the shape of this work envelope has to do with the kind of joints and their arrangements that we have. So for instance, if we have what we saw also in the first call, a Cartesian robot, which basically constitutes of 3 prismatic joints, so these 3 translations, we will end up with a box or a parallelepiped as the work envelope. So that's the volume that the tip of the robot, the end effector, can reach, right? If we have a revolute and 2 prismatic joints, we will end up with a hollow cylinder, right? If we have 2 revolutes and a prismatic, I will have something like a sphere, but with some gaps in between. This has to do with, I don't know, unreachable states, unreachable areas inside the work envelope. And if I have 3 revolutes, I'm gonna have a sphere, but with different sizes and different unreachable areas inside. This shape of this volume also has to do with the joint limits, how much the joints can rotate and other aspects, but this gives you an idea of, what are we talking about. All right. The work envelope shows us the volume that the robot can reach. However, we have to realize that the robot is not equally capable of operating in any point inside this work envelope, right? You can imagine that if I have my robot arm fully extended, yes, I'm inside the work envelope, but then I cannot wiggle around too much with it, right? So we say that we might lose a degree of freedom, right? We cannot do as many motions in this kind of configuration as we would be able to do if the joints are more bent. We will see more about this in lecture 5, I think, when we talk about the Jacobian. These are called singularities, and we'll see why they're called singularities and how we model them. What you should remember now is that we might lose some degrees of freedom in some certain configurations of the robot. All right? Great. Now, this is all about what we need about the modeling of the robot from the kinematics perspective. So let's see what is this forward kinematics. What do we call forward kinematics? So it's basically a tool, a mathematical tool, which helps us calculate what is the position and orientation of a point on the robot if we know the states of the joints, right? Typically, we care about the position and orientation of the end effector, but we can calculate the forward kinematics for any point of the robot, right? Another little detail here, and we'll use this word more and more. If we want to talk about position and orientation in one word, we typically call this the pose. Pose is position and orientation. So we don't always have to say position and orientation, we call it pose, right? It's a general term, right? So in simple words, the forward kinematics is a function that helps us calculate what is the pose of the end effector or any other part of the robot if we know what are the joint angles, or we will start calling them joint coordinates more and more, right? So for instance, an example, I have this very simple robot, right, with the 3 joints. There is one link, another link, and another link, and then the 3 joints. I know the lengths of the links. How do I calculate the pose of the end effector of this robot? Pose being the position and orientation of the end effector, right? Right. If we want to talk about position and orientation, what we saw last week, we always need some reference, right? We cannot talk about position without having some coordinate frame that we are expressing that position in, right? So we typically have a reference frame. Let's try to draw it here, that we put at the base of the robot. Right, and we're trying to calculate the position and orientation of the end effector with respect to this reference, right? That's the forward kinematics. How can we do this? Any useful tool we learned last week that can help us with this? Transformation matrices, right? Exactly. So we saw that transformation matrices are about describing a pose of a frame with respect to another frame. So that's exactly what we want to do. We want to express pose of the end effector with respect to another frame, right? So we use these transformation matrices, which encapsulate the information about position and orientation, or translation and rotation, in one nice package. Right, so we need to follow some steps. Let me draw a robot here. So we have it, I think I'll use it. So I'll draw this robot here as well. All right, and I'll use my friends from last week. So, what is the first step? We need to identify what are the links and the joints of the robot. In this case, we have joint, 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 link, link, link. Right? They're all 3 revolute joints on the plane, so the axis of rotation comes out from the board. And then we need to decide what is our reference. Here we are. So let's say, I don't know, we have something like this. Okay. And we do the same thing for every joint. I'm not going to do it for all the joints because I don't have enough. But I'll do it for some. So let's say I have one more here. Oops. And we also need to attach one at the end effector. So I'll do that here as well. So here I should have had two more, but you understand the logic. And then we calculate the transformation between subsequent frames, right? And we calculate the overall transformation by combining the frames, the transformations together, as we saw last week, right? So it could look something like this, right? Instead of having these frames, I have on every joint. Right. So let's see this very simple example. What would be, and here I have numbers as well. So I have frame 0, frame 1, frame 2, frame 3, and frame 4. So after I put my frames, next step is to calculate the transformation between subsequent frames. So I start with the base and I go to the first frame. So I want to calculate the transformation that takes me from 0 to 1. What would that be? A translation on Z by, it's not mentioned there, but let's say a unit, I don't know, 1 or 0.5. Let's say it's 1. Translation on Z by 1. Right? I'm not going to write the full form of the matrix. I have it on the slides. You know the form. Right. Good. Actually, yeah, you can see it here. So then I have the second transformation. I'm not going to move it. You can see it there. Which would be transformation from 1 to 2. What do we have here?
Translation again and rotation.
A translation on Z again. Sorry?
Just a translation.
By 2 units. And we don't have a rotation. Here I don't use the color code so that I have different colors for each frame, so it's more visible. But yeah, Z is pointing up, Y is pointing to the right, so we don't have any change in rotation, orientation. Right, so these are the first two. Then from 2 to 3.
So translation on Y.
Translation on Y by 3 units. All right.
And translation on Z by -1.
And then the last one is from 3 to 4. I have a translation on Z by, exactly because I go down on negative Z, it's going to be my -1. All right? Good. How do I calculate the overall transformation from 0 to 4? This is my forward kinematics. Multiply them. How?
From 0, so R01 times R12 times R23 times R3.
Like this? Right, that's correct. According to my very simple rule, these things will simplify. So I will have my transformation, right? Which would be how much? It would be basically this transformation matrix. Very simple. Which tells me what? That frame 4, with respect to frame 0, what do we know about the orientation?
Doesn't change.
They have the same orientation because here I have on the diagonal I have the identity, right? 1, 1, 1, right? And it's positioned at
Y and Z.
0 on X, so on the same ZX, ZY axis, ZY plane, sorry. And then it's basically these coordinates 3 and 2. y3 because here I just moved to the right by 3, y2 because here I moved by 1, another 2, and then down by 1. Right? So this is considered to be 1. All right. This is the rotation, the translation. Good. Now, quick recap. What do these numbers mean? Okay, px, py, pz is the coordinates of the origin of frame 4 with respect to frame 0. Right? y4 and 0 because I have 4 and 0. Right? And these 3 columns represent the coordinates of the x-axis of 4 with respect to frame 0, right? It has 1 on x, 0 on y, 0 on z, that's why 1, 0, 0. The coordinates of y of frame 4 with respect to frame 0, 0 on x, 1 on y, 0 on z, and the same thing with z, 0, 0, 1, right? Okay? Good. Now this is very simple, and we see that we calculate the pose. It doesn't depend on anything. It has some numbers because we didn't consider any kind of motion happening here. Like we wanted to calculate the pose of the end effector in this configuration. That's it. What if we generalize it and we calculate it for any rotation of all these 3 joints? How can we do that? Let me put these away. So now we'll need them. Come on. All right, so let's draw the robot here, more or less same configuration. I have this joint, oops, maybe too long, and then I have this. Right, now I measure Q1, which is this rotation from here. I measure Q2 from here, and I measure Q3 from here. And the goal is the same. I start from a base frame. I think I have it here now. So let's put it a bit down. And I want to calculate what's the transformation of a frame at the end effector with respect to this frame. Right, the logic is the same. I start by identifying what are the links at the joints. It's the same links, it's the same robot basically, but in a different configuration. And I go and put frames on each link at the level of the joint. Right? So here, for instance, I would put something like this. I'll put it a bit lower here. And I'll move once we need more. Good. Again, I have frame 0 here, frame 1, I will have a frame 2, a frame 3, and eventually the frame 4. All right. Let's start with the first transformation, R01. How do I calculate what's the transformation that takes me from 0 to 1? I have a translation. These things are not, they're not in the same origin. Translation and a rotation. What happens first? What happens second? First the translation. So let's say Translation along which axis? Z, let's say by 1 unit. And then
Rotation around X.
a rotation around X. From left or right? So I have to combine these two, right? To calculate the overall transformation from 0 to 1, I have two elementary transformations, a translation and a rotation. And I need to combine them by multiplication, right? Do I multiply from the left or from the right? From the left, Y. So you say rotation around X by Q1. Why from the left?
Because then the rotation takes to be around the base axis, not the.
Which one is the base axis? This one or this one?
Translate.
All right. So around the translated axis, right? So we start from 0, right? And we say we do a translation on Z. Then around which X do I want to translate? This one or this one?
The first one.
The top one. Let's call it the top one, right? So I want to do this. All right? In that sense, its own axis, exactly. Then we need to rotate around, we need to multiply from the left, right? So that's correct. Very good. If I would have multiplied from the right, what would I have done? I would have rotated around this X, so I would have done this rotation. So I wouldn't have ended up here, I would have ended up here. All right? Good. Okay. So like this. Now I said I use this magic word, first translate, then rotate, right? And I think I mentioned it last time that there is no first and second. It's all a matter of defining whether I multiply from the left and the right. Let's do a thought experiment, as Einstein would do. Right? Let's say I first rotate. So I don't do the translation, I first rotate. So I'm here, boop, 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 and then I rotate. Can I end up in the same, with the same transformation by first rotating?
Yes, I have to translate, but multiply from the right.
Right? So I have to translate again from Z, right? By multiply from the right. Why from the right?
Because I want to move along the parent axis.
Around this axis, not this axis. So if I multiply from the right, I will end up doing this, right? Not this. And obviously, if I multiply from the right, I will get to the same position because I'm doing the same thing, right? Whether I first translate and then rotate from the left, it's the same thing as saying I first rotate and then I translate from the right, right? It should be the same thing because it's the same numbers here, right? But you know, often I feel I had this discussion with students like, okay, do I first translate and rotate? It doesn't matter. I mean, you can say I first do this and then do that, but then you have to specify whether you multiply from the right or from the left your second action, right? But there are two different ways of seeing the same multiplication, right? It's saying like 2 times 3. Do I multiply 3 with 2 or 2 with 3? Yes, it's the same thing, right? Different ways of seeing the same thing. All right. There is no golden rule that I always translate and then rotate from the left or from the right. Whatever. You have to think of it case by case, so that it's you know, you're safer and not make mistakes on the transformation. In this case, I rotate and then translate multiplying from the right, or I translate and then rotate by multiplying from the left. I have the same result. How you're going to transform that into words is another story. All right. So this is the first transformation. Let's move on to the next one. And I'll use this one for now. Now I'm here. Come on. This is pretty bad. And then let's put this here and put this here. One small detail, I mean, probably you noticed, here I have a variable rotation, right? Because I don't know how much Q1 will be. It can be 10 degrees, it can be 30, whatever, right? It's a variable. So here's a variable. Right, so what's the transformation that takes me from 1 to 2? So R1, 2. First translation or rotation? However you want. Okay, let's say rotation around which axis?
X.
X by how much? Q2. And then translation. So now if I just write this, I'm here but just rotate around X. And then translation around Y. But which Y?
The first one.
The one from frame 1. Right? So I need to multiply from the right by L1. Sorry. By L1. All right. So I rotate first and then translate from the old Y. I come here, or I can say I translate around the Y and then I rotate from the new X, so I multiply from the left. Same thing. Okay? Good. You're getting this. And transformation from 2 to 3. What do I have? Okay. In this case, it's minus Q3 indeed. It goes in the other direction, but it's a variable anyway. So it can be positive, negative, right? So that's why I just write Q3. Right? And left or right? Right. Same reason by L2. From 3 to 4. Yep. Translation on Y by how much? Translation on Y by L3. All right. Right. Good. How do I calculate the overall transformation from 0 to 4? Same as before. R0, 4, R0, 1, R1, 2, R2, 3, R3, 4. Okay. Now, if we do this multiplication, and I have it here, so I have the frames, I have the transformations. So I think they're wrong. I end up with basically something like this. Yes, small notation here. I think this is wrong. I'll fix it. So I don't remember if we mentioned it last week, but C1 is cosinus of Q1. S1 is sinus of Q1. All right. And if I have CS1 virgula 2, it will be sinus of Q1 plus Q2. Okay, this notation just so we keep the transformation matrix a bit more compact. So if I do this multiplication, I will end up with something like this. This 4x4 matrix, right, which shows me the orientation and the translation of the end effector with respect to, of the end effector frame with respect to the base frame, right? C1 to 3 is cosinus Q1 plus Q2 plus Q3, all right? What we see here is that now we don't have fixed numbers, right? This is, all of them are changing, and it's they're changing based on joint coordinates, the angles, right? It makes sense because the position and orientation will change according to the joint angles, right? That's why we say that the forward kinematics is a function of the joint positions, angles, we call it coordinates more and more, and the lengths of the links, right? Here, these translations, the L1, L2, L3 will come into the transformation matrices. Obviously, it will make a difference if I have a long link or a short link, or different number of links. But these don't change during, while the robot is moving. We don't have changes of links. It's just the joints that move. So yeah. All right. And we saw here how we calculate for the end effector, but I could have calculated for any point. I could have considered that my robot ends here. If for some reason I wanted to calculate what is the pose of this point, let's say for collision avoidance or for planning or whatever, then I could have calculated the coordinates, the pose of this point, not the end effector, right? Okay. Good. Any questions? Yes?
Regarding the previous slide, I think the order of the translation and the rotation was different from the one.
Yes, I said this is wrong. I'll fix it. I realized I don't know how it crept in. Is this wrong or this wrong? Wait a bit. Because we say we translate on Z and then we rotate. We did this wrong. This is wrong. Aye. Sorry. My bad. Because we started with this and then if we multiply from the left here, wait. So if I do the translation, hey, why are we doing this? This is wrong. If I do the translation and I multiply from the left, then I'm rotating around. This is the absolute rotation. If I multiply from the left, I'm rotating around this axis, right? So I have to multiply from the right. Very bad. So the slides are correct. This is wrong. Sorry, I got carried away. So here, this has to be like this. My bad, right? I'll show you the video from the beginning. Multiplication from the right is relative rotation, relative transformation, right? Multiplication from the left is absolute. Sorry, I don't know what I was thinking. We have it on camera, so you can blame me at the end of the semester that I took it wrong. But yeah. Let's see. So now both these two show the same thing. Okay. What I was telling earlier about whether we do first this and then that, it still holds. So the same, but yeah, we have to remember what's right and left multiplication. My bad. All right. Why multiply from the right its transformation? So basically, why do we do this? So if I have, let's say, this transformation, and I want to go here, why do I start from R01 and I multiply from the right R12? That's because it's exactly the same thing. Now, I know how do I go from this frame to this frame, right? So if I do the transformation from 0 to 1, and I'm already at 1, I need to translate around the axis of 1 to go to 2, right? Because I wrote this transformation from 1 to 2, right? That's why I multiply from the right. So I start by R01, and I multiply from the right 1, 2, because this is the transformation with respect to the axis of 1, right? If I would multiply from the left, it would be happening all the transformation around this frame, and that I don't want. All right, any other questions?